Hello, everyone. Hey, Torsten.
Hello.
All right. What's the time over there? Hey, Torsten.
It's nearly 6 p.m.
Okay, it's a good time.
Hello. Exactly.
What's the time over there? Hey, Torsten. I
It's
think
nearly 6 p.m.
okay, it's a good time.
Hello. Exactly.
What's the time? Okay. Actually, I was streaming to YouTube. That's the reason there's echo. I just closed it.
Yes, it was kind of strange.
Congratulations on the recent huge award.
Oh, thank you very much. Thank you very much. Yes, that was quite a surprise and nice.
Very well deserved.
Thank you. Okay.
So, I guess you have a few minutes.
Mhm.
We can wait a little bit until the audience join, and then we can start.
Mhm.
I have a quick question.
Mhm.
So how many students do you have right now?
That's a good question. It depends on how you count. I mean, the ones that I'm paying, it's like 12-ish or so. But then there are many master students and others.
I see. Okay.
Let me actually.
So
Yeah. Yeah.
Sorry, I don't understand.
Siri, easy.
Huh?
That considered to be big in ETH reach or
It's normal. It's not big, I would say. It's normal.
okay. Previously, I thought you have a lot of students. I remember like
It,
20.
it's well, this is what I'm saying is a lot of master students and so that look like a lot of students to the outside, but yes.
I see.
And what we do is we encourage our students to publish very early on. So many master students actually have quite impressive papers. So
Right, because I saw you been quickly arising in HPC machine learning since 2019, 2018. I saw so many papers.
Mhm.
And what's FPGA, linear algebra, all sorts of different things.
Exactly. Yeah.
Yeah,
Well, these are all the great students that we have. So.
very cool.
I'm just giving them ideas.
That's very important. Yeah. So they can make it moving forward. That's very important.
Mhm. Exactly.
So this is the background is like your institute.
Yes. That's ETH Zurich here, the
I see.
building. And that's the neighbor university, actually. That's the University of Zurich. So we're very close to. They're not to
Oh,
be confused. There are two different universities.
okay.
Can you hear me well? Is the audio quality reasonable?
It's perfect. Very
Oh,
good.
wonderful.
Yeah.
Wonderful.
So right now, you guys are working on prompt engineering a lot or agentic AI?
Less so, actually. We were mostly working on reasoning models and basically this graph of thoughts stuff. So trying to understand how to get models to do more advanced stuff without prompt engineering. That's exactly the point. And essentially without agentic approaches as well. But that is harder because agents make a lot of sense if they're specialized to certain things like a web agent or a retrieval agent, or I don't know, an agent using a calculator and things like this. However, some agents are basically primed language models that are primed in different ways. So that's not what we do.
I see, I see.
Yeah,
Yeah,
there's
it's for hardcore HPC folks, it really will feel like a little bit hard for us to, move to prompt engineering completely.
yes,
Sounds like what
exactly.
we are sort of discarding what we learned, this heavy sword
Hmm.
to some little stuff. Students
Yeah.
also been struggling. I mean, when it goes to really big training things, students feel it's too monolithic. But when it
Hmm.
goes to prompt engineering, they feel it's too trivial or it's too hard to grasp what are the real system contributions. Those are the things I think we've been facing right now in HPC.
Exactly, yes.
Yeah.
And it's always a mix of the two. You'll see it in the talk that we're basically working on the data science as well as on the HPC side. Because of course the best tricks you pull will change the data science slightly, and then you have to get back to the best results. So that's always the fight.
Yeah. We've been feeling the same pain as well.
Hmm.
Um,
Hmm.
I think let's probably wait for another 2 minutes.
Oh, sure.
Right. So quick question for the ACM award in computing, that a 250,000. So that goes to your own pocket or goes to your institute?
I think so. I still need to understand this. It hasn't been it hasn't been awarded yet, so
I see.
not 100% sure.
That's a whole lot of money.
Hmm. Yes. I mean, Turing Award gets 1 million. It's probably the same conditions. I have to check. And I didn't have much time yet. Since then I'm traveling, and
This is a warm up for you.
no, no, but since the announcement, I didn't have a whole lot of time thinking. I signed up for all kinds of things like this one here, and so I can't take a break. I can't even really think.
So
So,
so when's the time for the ceremony?
June
Where?
in San Francisco.
I see. Wow.
This
Cool.
is the standard ACM award ceremony, the annual one.
Okay, that goes together with the Turing Award.
Yes.
Wow.
It's with the Turing Award and all the ACM fellows and all that.
Oh,
Basically,
wow.
all big ACM. And I think it's really only Turing Award ACM fellows and pricing computing. All the general ACM awards
I see. Oh,
that
that's
are
that,
not
that's a
SIG
huge
specific.
event. Yeah, huge
Mhm,
event.
mhm. Yeah, it's a pretty big event. Yes.
Okay. Let's probably start right now.
Mhm.
Do a brief, short introduction. I know there's so many things about Professor Hoefler, right? So, Torsten Hoefler is a professor from computer science at ETH Rich. He's a fellow of so many things, European academia, European fellow of ACM, IEEE, Alice. From my perspective, when I was a student, okay, I read a lot of papers from Torsten. So he has won a lot of best paper awards from SC several years, I would say, and also chairing the SC supercomputing conference, winning those flagship SC awards like the Sidney Barch Award, ACM Gordon Bell Award, Jack Dangara Award, so many. And recently, I just talked about is ACM Award in computing. That's a 250,000, reward recognition. Without further ado, Torsten, the floor is yours. Thank you for being here.
Excellent. So I'm very happy to be here. Thank you very much for the invitation. And I'm going to talk about the HPC aspect. I know the seminar is called Challenges in AI Ethics and HPC. So my background is high performance computing. I've been working on it for a very long time. My home conference and home community is the supercomputing community in ACM. We're the SIG HPC. So I'm going to focus mostly on the high performance computing aspects. I'm going to go a little bit into the data science aspects because it's a necessity to focus on the high performance computing aspects to do this. And what I want to do is I want to actually start relatively early on. So, so let me start with the very beginning, the age of materials, when in the Stone Age, the first humans were actually learning how to use stone materials for their help. And now this is going to be a very long talk. You can see this, right? But no, I'm going to move fast. So humans went through the Bronze Age, through the Iron Age, And then we invented construction and manufacturing. That's quite of an interesting change. So we were basically using simple materials, but then we built from those simple materials pretty impressive objects like the aqueducts, windmills, machines, and essentially in the Industrial Revolution, not too long ago, 1900, we made a step that is really remarkable. And that remarkable step was that human physical strength stopped being completely irrelevant. Any of us can operate machines that are significantly stronger than ourselves and actually significantly stronger than dozens of humans or even hundreds of humans if you operate ships, for example, or thousands of humans. So that is an insight that I want to push forward a little bit, because if we now go into this age of technology, of course, human development did stop at 1900, but we continued in 35 in the atomic age, space age, the digital revolution, which is where I somewhat grew up with, the information age, and then the data age. And what really happened here in the last 3 steps in the digital revolution, we learned how to use digital circuits. In the information age, we learned to use these digital circuits to gather information and to connect ourselves, like the internet happened in the information age. And in the data age, we learned to value the immense amount of data that we have created using those digital circuits with the networking in these digital circuits. And that's where many people believe we are right now. And there's one question I want to pose here at the very beginning of the talk, and I will not answer it, but I will want you to think about it. When will human creativity and intelligence become irrelevant? Right? We have already made human strength irrelevant. So when will we make other things irrelevant? So, and I'm posing it as a when, not as an if. I'm pretty convinced this is going to happen at some point. The question is when. So let's move this up here, and let's now actually argue that we are already behind the data age. So I actually claim that we are already in the age of computation. So what does that mean? So we created digital objects or digital computers. We create a lot of information with them. Then we realized that the data we created as humans is actually extremely valuable. And now we are in the age of computation, where we realize that the computation itself can create more data to be even more valuable. And this is what I want to push in this talk and give you a little bit of the history of how I believe this happened. So many of you probably know this company. Usually when I give this talk in person, I'm asking who knows this company. And then, I mean, if not everybody lifts their hand, usually they don't belong to this audience. So NVIDIA is one of the most successful companies actually in human history in terms of growth, speed of growth. If you look at the market capitalization, it's amazing. And well, as of yesterday, it's not so amazing anymore. And I hope you don't hold too much NVIDIA stock or any other stock, but well, things happen. But it used to be last week the second largest company on the planet, and it probably still is because stocks have been falling equally well for everybody, and it has shown the fastest growth in human history. So that is quite interesting. NVIDIA as a company does not build storage products. So it solely builds compute accelerators, or most of its revenue come out of compute accelerators that are used in graphics, that are used in deep learning. So that is one piece of evidence that we are probably not in the data age, but we are actually in the age of acceleration, in the age of computation. Another piece of evidence is if you listen to Sam Altman, who about a year ago said that 1 year ago, right? OpenAI generates 100 billion words per day. All people on Earth just speak 1,000 times more. Now imagine what happened the last year. I mean, probably by today, AI models are likely to generate more words per day or per minute or per time interval than humans speak on the planet, including me here. So that is quite interesting. Furthermore, people have now, of course, realized that we could run out of data because we have fed all the data to AI models, and people were predicting this a while ago in 2023, actually, to be 2026, so next year. In fact, people believe that synthetic data could even be better for training AI, and that is a huge opportunity. And what does that mean? So, for example, if you want to build an AI scientist, a scientist by definition is a person or an object that creates new knowledge. So I'm a German native speaker, and science literally means Wissenschaft. If you're a German speaker, you would understand this. But if you translate it word by word, it's 2 words. It means create knowledge. And it's implied that you create new knowledge. So how can an AI model create new knowledge if it's bound to the data that humans have created before? Obviously, that's not going to create an AI scientist, but AI models can generate their own synthetic data, which many people don't like. This is often called hallucination. So in some sense, if an AI model creates a fact or no, states something that is not in the knowledge database, people call this hallucination and they don't like this. But people more and more realize that this hallucination is actually a useful or could be a useful property if used carefully. Of course, if you're asking for facts, what is the capital of France, and it tells you Belgium, oh, that's not useful. But if you ask an open-ended question, and it could generate a hypothesis and then prove the hypothesis, this could actually create an AI scientist, which is very, very, very valuable, because then we could basically outsource much more than human physical labor, also human mental labor, to computers. And we've been contributing to this area with a paper that we call Graph of Thoughts, which basically the idea is a following chain of thoughts where we invoke the language model iteratively to solve more complex tasks and argue with itself, or argue with a family of models. So in some sense, I'm claiming that computation is really the new oil. It's not the data anymore. The data is somewhat exhausted. And the good news is anybody, including the little country of Switzerland, can now create oil by investing into computation. And many people have understood this, and many people move forward. And now I want to go a little bit forward, but many people at this point would ask, well, with this NVIDIA, we have seen some interesting thing happening. Actually, in January, NVIDIA lost nearly $600 billion as a Chinese company shows up and says, hey, we can do that as well, basically. And hey, we can do that a little bit more efficient. It wasn't much. It was about a 50 times more efficient. But hey, that's quite interesting. Costs NVIDIA alone $600 billion. Cost a huge shock to the US stock market. And it was quite interesting because the company called DeepSeek released their technical report actually already in December 2024. And so what they basically said is that they used a cluster that is made out of rather weak GPUs to train a model that is somewhat competitive with the best models known today, even closed source models. So that was a shock. And they claim that they have trained it at less than $6 million, where everybody else spends significantly more. So now, of course, there are a lot of speculations. What happened? Also turns out that the head of DeepSeek is a hedge fund manager, so you can create the story yourself. But this is a lot of interesting action going on in this area that I just wanted to mention. But now let me go back to the history of this essentially intelligence that we were building. And I don't want to go to the very beginning of the history because I already told you about the Ice Age, the materials ages and everything. I want to start in 2017, where there was one breakthrough paper which essentially replaced sequential models like RNNs or LSTMs with a parallel model. And this paper is called Attention is All You Need. And actually, at the very beginning in 2017, the scientists that did this, their main goal was to parallelize RNNs, to run them on architectures that at that time was a very parallel architecture, was a Google TPU. And they wanted to enable these models to run faster on TPUs. And so they changed the model architecture. This paper forms the foundation of pretty much all of modern language models and autoregressive models. And so how does it work? Well, it was relatively simple. They basically said, well, instead of feeding the inputs one by one into the model and transforming an internal state in an RNN and saving that internal state and generating the next with it and so on, they feed the inputs all in parallel through an input embedding with a positional encoding that the model could tell where which input is and blah, blah, blah. So you probably know all of the details. And then you would go to an output. So if you think about this, each of these boxes are very, very, very simple operations. Like this multi-head attention is nothing but a little bit of a scaled dot product, some linear layers, some vectors moving in. We have a concatenation layer, another linear layer. Each of those are close to trivial. Like at the bottom, we have a matrix multiplication, a softmax, which is a very simple operation, a mask, which is even simpler, and then some scaling and another matrix multiplication. But at the end, what these models enable is they can take a tokenized input text and they could translate it and they could complete a translation, and here from English to German, with the most likely next word. That was the original task they were trained for translation tasks, because LSTMs and RNNs were translation tasks. At the time, the Google team who did this wanted to build a better translator. That was the goal. But now, what turns out that these models are near trivial in the terms of computation. You could really explain it to your grandma. I mean, if your grandma would listen long enough. And at the end, it also turns out that 95% of the operations are just matrix multiplications, the arithmetic operations. So that makes it a great fit for HPC GPUs, easy to parallelize. You can see how NVIDIA is so successful in this area because they really offer the architecture for this matrix multiplication, which actually is really derived from a graphics pipeline. So they were aiming at making graphics fast at the very beginning as a side product. They turned out matrix multiplications. Then later, the HPC community was picking this up and saying, hey, we can use these matrix multiplications. So this is how the Tesla product line in NVIDIA came into place. And that at the end benefited much of deep learning. In fact, for the massive progress in deep learning, I would credit the HPC community significantly under the leadership of Jack Dongarra, who also very much deserves the Turing Award that he got for this later, because he was pioneering all of these fast libraries that are now driving essentially all of deep learning. And now, how does it actually work? Well, we take this text, we encode it as a token, which is extremely important, and I don't actually have enough time to explain it in great detail, but people use something that's called BPE, byte pair encoding. It's a very simple strategy again, but lots of data churning. So you look for most common substrings, and there's a very nice paper for Tvec with 45,000, more than 45,000 citations. Very, very nice, very, very old, very foundational paper. But at the end, what we do is we take these words and turn them into vectors. And then we simply do, I just wanted to say linear algebra, but it's not linear algebra because it's not linear. So we simply do transformations on these vectors with these transformer structures. That's the computational problem. But now, what did we do with it? And that's quite an interesting story now, also from an economic perspective, because 2017, these transformers came out, a Google paper. 2018, another Google team was actually looking at using these transformers not just for translation, but to understand language. They wanted to see if you could actually generate a semantic understanding of what words are in the English language. And so they did this with a very simple masking task, and they found that yes, if you train a simple decoder with enough, oh, sorry, it was actually an encoder, with enough language, text, then it would be able to guess simple semantics. So it would understand some form of language. And that was very interesting. Unfortunately, or fortunately for everybody else, but unfortunately for the company of Google, they didn't take this very serious, and they basically said, well, you know, that's a nice insight, wonderful, gets a lot of citations later. There was another company, OpenAI, which you may know, that took this idea and drove it to the extreme. They basically said, well, we do a decoder. We learn a language completion task. So, and we just bet the farm, we bet everything we have on running a lot of data through a language completion model that learns the statistical distribution of language from the vast corpus of data that we have, and turn this essentially into an unsupervised multitask learner, which means that it gives you the completion of the most likely completion of sentences. For example, if you wanted to know what the capital of France is, the hypothesis at the time was you would phrase it not like a question, but like a completion task. You would basically say, the capital of France is, and then you ask the model, what is the next likely word? That was the vision at the very beginning. And that actually worked really well. And that's an unsupervised multitask learner because you can phrase many, many, many tasks as such completion events, right? Or such completion tasks. My car is broken. I now want to go to the, well, dealer or something like this. Then later, they simply scaled this up. So GPT-2 was a big success. They scaled it up, and then they realized language models are actually a little bit more powerful. They can even do more than simply completing language. They can actually perform a few-shot learning task. What does that mean? In a few-shot learning task, you give the language model more input. So you basically give it a lot of examples, like poor English input, good English output, poor English input, good English output. You give it a lot of examples, and then you give it the task that you want the model to do. It's basically the next step after completion stuff. And then it'll give you a good output with the context of all these examples. So that is quite interesting because that now makes it very useful suddenly, right? So you can now say, oh, wow, I can give a lot of examples and it'll find the pattern and complete the examples. What happened then was basically a game of scaling. People made these language models bigger and bigger and bigger on faster and faster computers. So here we see the validation loss, which is a metric of quality. So the lower, the better. And here we see the compute time invested in training a specific model with a specific number of parameters. Each of those lines is a specific number of parameters. And we can see there is a scale here of petaflop seconds per second per day, or petaflop per second days. So here, this 10 to the 0 is 1 petaflop per second used for one whole day. Just to give you a little bit of an understanding, I'm not that old, but maybe I'm that old, depends on how old you are. So about 10 years ago, I was a member of the Blue Waters team at the University of Illinois, where we built the fastest computer on the planet, essentially the Blue Waters machine, which was a sustained petaflop per second machine. That was 10 years ago. The fastest machine on the planet did 1 petaflop per second, and you would need to use that machine for one full day to train a model at that scale. You see, that is 100 of those here, and that is 10,000 of those. You see how fast compute has developed. That's completely crazy, and it's very, very expensive. You could also see that actually the entropy, the cross entropy loss, which is another metric of performance, so the lower the better. Again, it's a loss metric. The more tokens, the more text you feed into the model, the better the quality gets. But you can also see it's kind of tapering down, so it's a logarithmic curve here. At the end, there is a very famous paper that drove much of the industry, scaling laws for neural language models. And what they realized is larger models require fewer language input samples, and the optimal model size grows smoothly with loss target and compute budget. That started the AI industry, basically. And from there, it was all a crazy history in some sense, because now suddenly companies like Microsoft popped up. For the first time in history, a private corporation invests a huge amount of money, $1 billion, into a supercomputer. And they basically invested into OpenAI, but at the end, they built a supercomputer, and everybody is now talking about supercomputers. So for HPC, that was the most interesting thing that happened in my career, at least, because HPC used to be a government-driven scientific computing business, but now it's big industry. Google has a supercomputer. Facebook, a social media company, has a supercomputer. Actually, Tesla, a car company, builds the supercomputer. How does that make sense? And if you look at the total number of GPUs purchased, it's also quite interesting. So an NVIDIA H100 GPU cost about $10,000 at the time. And now look at the two companies, Microsoft and Meta. In 2023, they purchased 150,000 each. And now think about this, right? You could also see many other companies, Google, Amazon, Oracle, Tencent, Baidu, Alibaba, ByteDance. In 2024, it switched. You can also see geopolitical movements here. Microsoft bought nearly 500,000 GPUs. But now number 2 is ByteDance, Tencent, and only then Meta. So the Chinese colleagues have been ramping up their business very, very quickly before, unfortunately, they were hit by not being able to buy those GPUs anymore now most recently. But that's an interesting development. Microsoft talks about the age of AI and pledges $80 billion just in 2025 to invest. Of course, the US government has to have a bigger goal. That's $500 billion, so $500 billion into AI hardware, AI computing. So what is this all about? So what are we talking about? Actually, we are still talking about the same thing that I talked at the very beginning. We take language of the internet, we remove a word from the language of the internet, we run it through the transformer model that I showed you at the very beginning. It's still the same model, nothing much changed. This model produces an output distribution over all possible output tokens. So here I'm just showing 7, but actually this would be a dictionary of size 80,000 up to 100,000, depending on your language. And then, of course, you know what you removed, right? So harm in this case was removed. What you do is you do a layer-wise weight update for the next iteration to be more likely to boost the probability of harm, because this model creates a whole lot of learnable parameters. And then you do this millions, if not billions of times. Like you run this loop many, many, many times. At the end, if you want to go into numbers, we train today, actually 1.4 trillion tokens is long the past. We train on tens of trillions of tokens today, and it's really the whole internet that we are exhausting. We are running extremely large models, like for example, models with 540 billion parameters. That is a very large number because just storing these parameters in FP16 is 1 terabyte. Do you have that much main memory in your accelerator? No, nobody has that much main memory. So we need supercomputers to just process these models. And it takes weeks on these supercomputers to run, to train these models. Great news for HPC. So now I want to go into a little bit more technical detail on how do we actually optimize these transformers. And so if you look at these transformers, well, it's still relatively simple. They are very important. 175 billion parameters costs about $12 million to train, just to give you some number. That was back in 2019. Of course, now it's much cheaper. But now we train also much larger models. So we're still in the same ballpark of double-digit million dollars. Then if you analyze these models in their computational requirements, you find that tensor contractions, basically matrix multiplications, that's a matrix multiplication, they are 99.8% of the arithmetic operations of a model evaluation. And then you have two other forms of operations, statistical normalization, which is basically layer norm or softmax, and element-wise operations, which are like ReLU, GLU, and all these nonlinearities. They're only 0.2% of the total number of operations, right? So this is great. However, tensor operations have been highly optimized. Like, this is what tensor cores do. This is what everybody tunes for, thanks to Jack again. Jack Langara has been driving that. And the unfortunate thing is now that these are heavily optimized due to an Amdahl's law-like effect. These 0.2% of the operations causing 40% of my runtime, nearly 40%. That's pretty sad, right? So I would expect this to cause 0.2% of my runtime, but it's nearly 40%. And this is not arithmetic operations that happen. This is simply data movement that happens, because data movement is extremely expensive. And if you want to see all the details, there's a paper here with the archive link where we explain this in great detail. At the end, we do data movement optimizations. We don't care about the computations, but we get a 30% speed up over PyTorch and an 8% speed up over the manually tuned deep speed version at the time. Today, this is all implemented in any framework, so this is standard, but this would save large money. But I just want to tell you about how we did this in 2019. This is quite foundational to how AI works today. First of all, you look at the computational graph. Now you have certain inputs and certain outputs. This is just multi-head attention. I don't have enough time to go into details. You can read the paper and find out exactly what it is. But at the end, there are always inputs, there's an operator, and then there's an output. That output is consumed by another operator as input. Right? So it's a computational graph. It's not super complicated. But now each of these operators is working on matrices or on tensors. So you see three dimensions here, P, I, H, and I, and I, B, and G, I, B, and J turns into P, H, B, and J. This is, by the way, Einstein notation, in case you know tensor contractions. And this is quite versatile. You can actually transpose these matrices in different directions. So you can store them in different ways and in different data layouts. And if you look at the specific performance from the worst performance to the best performance, depending on just how you store these matrices in main memory, you see a factor of 10 on this V100 architecture. Another thing you can do is you can now fuse these operators together in single loops, basically. Do you implement this in one loop, or do you implement this whole thing in one loop? Like these are operator fusion strategies. You again see a factor of at least 10 to 100, depending on different fusion strategies. So then, of course, you can enumerate all the possible data layouts. You can enumerate all the possible fusion strategies. It's an exponentially large search space, so it's no fun to search it. But we have some tricks for this. We basically built this configuration selection graph where we optimize for the best data layout and the best fusion strategy, do an automatic search on the supercomputer, and this is how we get the speed up. And we beat actually all the humans that have done this, because a human only looks at the intuitive subsets, and so the automatic search found some unintuitive subset. So all of these ideas are in production today. This works great. And we realized at the time that we really need to reduce the cost to continue scaling, because what we want is to want larger and larger and larger models, but they're already tens of millions of dollars, so we need to go on. So now back to the timeline. We have been in the era of model size scaling. The major interest at that time, up to 2020, was to build bigger models, because at the end, bigger models had bigger capabilities. So they were doing more stuff. So the hope was, at some point, by just scaling the model size, we would reach human level performance in pretty much everything. That was the hope. And then 2022, what happened there? Well, people actually discovered that you could turn these pretty lame completion models into a nice chatbot. So new techniques were invented, also in the realm of OpenAI, but also many others. RLHF, reinforcement learning based on human feedback, was basically like you would educate your child. You know, if your child says something stupid, you say, "Oh, stop this." If your child says something nice, you say, "Oh, good, keep going." And so in RLHF, you do this with a language model. You basically say, "Well, are you a nice chatbot or not?" So people vote on this, and at the very, very high level. And this training helped the chatbot or the language models to behave like a nice conversational partner. Later, that was replaced by DPO, direct preference optimization, because RLHF is a little bit expensive. But doesn't matter. At the end, we were able to turn these language models that were simply built for completion into a nice conversational agent, actually an instruction following agent, so something helpful. So now suddenly that thing turned into a business, right? So suddenly there were millions of customers waiting for ChatGPT or using ChatGPT every day. And that was a very fast growing business. I don't have the statistics here, but it was one of the fastest growing businesses ever. Because of course they gave it away for free. And if it's free and useful, everybody wants to use it. That's pretty clear. But now what we needed to do suddenly, and I was partially involved in this, we need to enable this business. And now there came another player. The second player was actually Meta in the game. They said, well, we want to compete with this because we can also do language models. It's not a purely open AI thing. But how did they compete? They basically realized that with ChatGPT, it would be very hard to compete. But they said, we will make the whole world compete with ChatGPT. We will simply release our models as open source. We will run a Linux-like model. Sorry, open weight. It's not really open source. And I can explain the difference. We run a Linux-like business model and now have everybody use our open models. And later, many companies followed, like Qwen and Grok and many others, and also DeepSeek at the end, and build this open business, which put a lot of pressure on the commercial side to reduce cost. Now we needed to build smaller models, more better data, more training compute, and essentially optimize the model from a computational perspective such that OpenAI and others could serve those cheaply. Because at the end, we need to reduce hardware costs to compete in that market. So what happened now? We were basically ending the era of model size scaling, and we wanted to build smaller models. Because if you have a very large model, it's extremely expensive to use, like to generate tokens. You don't want a large model to generate tokens for 1 million customers. That's a bad idea. So you want to now make these models smaller. And you want to make them efficient and commercially successful, and that you can technically run them on your cell phone. So we went into a different mode. We now realized as a community that if we feed those models with more data, we actually overtrain them slightly with respect to the original scaling laws, they would become better conversational agents even with less parameters. So now we actually need more data, more compute when training the models, but less compute when using the models. So again, great news for HPC people, because now we needed even more data centers to do this. And of course, everybody now, latest in 2023, realized optimization is really the future of AI, because it's a very, very compute-intensive business. There's not much else. There's data curation, there's running large jobs, and there is the tuning at the end, but it's really about running the jobs at the end. So now this is where my group and I came in, and we worked on developing a scientific approach to do this optimization for AI. And I'm now going to give you a little bit of a rundown of how we were able to improve the cost, essentially with many collaborators in the field, and you will see all of those cited. By about 1,000 times. And this is what enabled AI as we know it today in many ways. So the first thing we realized early on, and I already talked about this in 2019, moving data is most expensive, right? That's quite annoying. Right? We have optimized it. We got like a factor of 0.5 out of this, great. But now, wouldn't it be much nicer if we would shrink the data that needs to be moved, right? So that's the obvious thing. And that's called quantization today. So if we want to run gigantic language models on reasonable systems, we need to use limited precision. And one interesting comparison point here is that the brains, like my brain, has very limited precision. My brain, in fact, has only 4.6 bits, is running at 4.6 bits. Yours is probably running at 5 bits, but mine is only 4.6. Because if you look in the literature, the typical human brain can only distinguish 24 voltage levels in the receptor. And that's about 4.6 bits. Why are we computing with 32 bits, right, in computers? Not clear. At the time, that was just a standard. But what happened is that we realized, well, if we have that many parameters, it's actually quite problematic because we need to store them. 1 terabyte in FP16, still half a terabyte in FP8. So that's quite tough. And now the question was, can we simply round these parameters down? Can we just represent them in FP8, for example? And the answer is pretty much yes. During training, it's quite complicated, but for inference, the weights, you can just round them to FP8 and do some tricks, and they'll actually be reasonably reproducing what the FP16 or FP32 variants did. But if you want to go to less than 5 bits, it gets quite hard. It's kind of an interesting insight that this 5 bits kind of correlates with this 4.6 bits up here. Most biologists tell me, that's probably nonsense, but I find this entertaining. Now, how do we get to less than 5 bits? Well, that's not so easy. But we've developed a technique together with Dan Alistar's team and Elias Franter, who's now at OpenAI, looking at the error landscape if we assume a model has been trained. So this is a one-parameter model. This is like a totally silly model because nobody has a one-parameter model. Imagine, instead of a two-dimensional space, imagine a 540 billion dimensional, actually 540 billion plus one dimensional space because you have the loss function as well. Okay, but I only have a 2D canvas here, so I'm drawing one parameter. How do you train a model? Well, you start at a random initial position of x, and then you do the gradient descent based on your input. So you go to some kind of local minima. Here, S1 goes to this, S2 goes to this. Okay, great. Now, once the model has been trained, we are down in a local minima, let's say here. And then we can expand the loss function with the Taylor expansion. We can basically look at the first order term, that is the gradient, and the gradient should be 0 if the model has been trained. We can look at the higher order terms that are more than second order. Those are actually 0 for quadratic loss, but for cross entropy loss, they're close to 0. That's just an empirical observation. For much of this is just close to 0. Now, all that matters is essentially the second order term that is non-zero. And now if you look at the second order term for a two-parameter model, now I suddenly can draw the third dimension as a whole here. So this is the minimum here, and this is the maximum. And I now ask you, if you had to round one of those two parameters, either x1 or x2, to the next representative number, where would the rounding error be smaller, assuming that's the same scale, same distance scale? Right? So I give you like 10 seconds to think about this. Which parameter would you round if you see that loss landscape? Of course, this loss landscape you would immediately see in the second order Taylor expansion. So at least at a point. So which one would you round?
Is it in the
What?
middle? Is that in the middle?
Sorry, what?
Is that in the middle of the oval?
Yes. So that's the minimum. But which parameter would you round? X1 or X2?
X2?
No, it's X1 because it's much flatter. Because when you
Wait,
round
I see.
the parameter, you move it to the next representative number on the number
Oh,
grid.
yeah, right. You have more
And then you
more
would
fine grain. Yeah.
Exactly. You would better sample that space. And that's the key idea of the method that we call GPTQ. It's quite a nice paper. I could now go more. I just wanted to give you the intuition, go more into the mathematical details. It's a post-training quantization. We play a lot of tricks because at the end we would have to solve the inverse Hessian to get the second order expansion, which is a matrix of size 540 billion times 540 billion. There's no computer on this planet where you can store this matrix, so you have to somehow approximate it, lots of approximation ideas. But we essentially get to 3 bits. With that at nearly no loss. We can also, with some more tricks, we can go down to 2 bits, but at the end we only needed 4. so everybody does 4 bits now because that's what the architectures do. But you can push this quite far. So that gets us from 32 bits to 4 bits, right? So that's a factor of 10. Okay. So now let's look how we go further. We have now just gotten the factor of 10. So how do we go further? Well, the second insight is my brain is not densely connected. In fact, if my brain is activated more than 20% on average, I have a seizure. So it's not good. So the brain is actually relatively sparse. Why are we using dense matrix multiplication for DNN and LLM computations? Well, mainly for technical reasons that I could explain in much detail. Actually, there is a whole other talk on this online on YouTube where I explain this in a 2-hour session in case you care. But the intuition here is that not all features are always relevant, right? So for example, you can read this. Can read the sentence. It's missing about 1/3 of the letters, but you can totally fill it in without any error. And this is basically equivalent to removing parts of the neural network and parts of the weights. And the key results of this is that we can actually sparsify many models to 95% or 90% without significant or actually without any loss. That means we are reducing the parameters if we get 90% sparsity by 10 times, right? So that's quite nice. Again, if you care about this in detail, this is a more complicated topic than the quantization. I don't have such a simple intuition. There's a survey which is actually the longest paper in JMLR, as far as I know. And there's also the 2-hour talk that I promised on YouTube that's called Sparsity in Deep Learning. And if you Google for that in my name, you'll find it. But at the end, there's a very nice iClear paper where we basically combine the two sparse quantized representations, so both sparsity and quantization, to get the combined speed up. So they actually combine. So that gets us 100 times, right? We've sparsified to 90%. We have quantized from 32 to 3 bits, essentially. So that's 100 times. How do we get the last 10 times efficiency? And that's a cost efficiency. So that's not a performance efficiency, but that's cost. Because now we process data more efficiently, which actually makes our data movement more important, right? Because now each of these matrix multiplications is 100 times faster, but the matrices are only slightly smaller. So that's unfortunate. So we now have to move all that data. It gets even more critical. So what we've done is we came up with a new network topology that, again, gets us a factor of 10 speed up in that sense. It's another paper that you could find on arXiv, was published at Supercomputing 1 year ago or 2 years ago. But the idea is very, very simple. So today, most people in data centers build fat tree topologies. These are essentially all-to-all connected through multiple stages, all-to-all connected accelerators. Each of these is an accelerator. Each of these things is a switch. And they're extremely expensive. What Google built a while back and HPC built a long time ago are so-called torus networks, where you only have a neighbor connectivity. So you put these accelerators and you only connect them with the neighbors. This was the TPU v2, I believe. That's a 2D. I think in TPU v3, they went to 3D because that gets a little bit better connectivity. And then what we came up with in a collaboration with Microsoft is that we actually combine the two. We take fixed sizes of torus networks, in this case 2-dimensional, and we combine them with a switched network. And then you can have the trade-off. You can run one extreme of the Hamming mesh is a fat tree topology, another extreme is a local torus topology. And now you can dial it freely. And it turns out that this idea of having connected, like fully connected islands of a torus, or actually in this case mesh boards, is able to reduce the cost by about a factor of 10 to actually 10 to 15 times. Because you can play a lot of tricks, because these local links are extremely cheap because they're usually PCB connections. And if you put two accelerators next to each other on a board, the link comes for basically free. And now you can build 4 or 8 or 16 of those, and then you can connect them with a rack, and you can see where this goes. So it's quite nice. You also see lots of these similar topologies now being used in practice. Actually, Google later built their TPU v4 or v5, I'm not 100% sure, with a very similar topology, just optics. So now we have looked at the 1,000 times speed up with scientific principles. I haven't talked about I/O. There's another talk of me where I talk about I/O. I've talked about high-performance computing and high-performance communication. If you want to hear that full story, there's another YouTube video, which is just 1 hour in itself, where I'm explaining all the details of this. But this was just an overview, because this is just showing that we could actually make this thing 1,000 times faster, which is enabling now something that I want to tell you about, which is absolutely mind-boggling, at least in my view. So what is happening now? Because we're in 2025 now, right? So 2023, the world didn't stop. Well, what happened then is actually very famous people said, well, we will end the data. We will exhaust the data. We only have one internet, and the internet is not growing fast enough. At some point, we will have all the data on the internet in the language model. Actually, there are language models that are close to this. Many of you have seen this graph from the GPT-4 report, where we look at the ability of the language model to perform in human exams, multiple choice exams, your various exams, and compared to the percentile of humans it performs at. So basically in the GRE verbal, the language model here, we just look at the highest bar, is at the 98th or 97th percentile of the humans. So only 3% of the humans are better in GRE verbal than the language model, which is crazy, right? And now this is the 50th percentile. So this is kind of your average human here, right? So 50% of the humans are better, 50% are worse. And you can see that the language model is better in most exams, and actually 2/3 of the exams, than half of the humans, which is crazy. Now, my statement is that LLMs are great at knowledge because these are all knowledge tests, exactly. These are kind of these not so interesting tests where you ask book knowledge, but they're bad at reasoning. So let me give you one example. So if you did ask a language model 2 years ago, this question, sort the numbers, 3, 2, 4, whatever, any sequence of numbers that's long enough, the language model would struggle incredibly with this and basically do random stuff. Because what it was looking for is the most likely next word prediction. And of course, this doesn't make any sense because it has never seen this sequence before, because this sequence is likely not on the internet, right? So it could do knowledge tasks because they're all on the internet, but this sequence it has never seen. So now how do we get the language model to work on reasoning tasks that require applying some kind of intelligence, what we would call intelligence, not just look it up? Well, there was a very interesting paper in 22 that's called Chain of Thought. The idea was you basically give the language model kind of an instruction, like you would tell your child, well, in order to sort these sequence, you do the following steps. And then you give it a task. And actually, it turns out that with that kind of instruction, like you train your language model like a child, the language models were becoming better at these reasoning tasks. And it turns even out that these instructions are in the knowledge base of these models because there are descriptions how to sort in the internet, right? And then there was a very funny paper where literally you just prefix your language model prompt with do it step by step. And the language model just magically started to understand, to look up internally, like step by step. Oh, I have a step-by-step method to do this task, blah, blah, blah. That was really mind-boggling. I mean, when I learned about this, it was completely crazy. But it's actually happening, and I can now more or less explain it. So this launched a whole series of work. So multiple chain of thoughts, where you have various options and do a majority vote. We had a tree of thought work where we reuse thoughts across different reasoning paths now. And then at the end, we had our work, which is graph of thoughts, where we basically could combine in tree of thoughts, you have only a reasoning path, but we could combine two different reasoning steps into one reasoning step to move forward. Like I have lemma 1 and lemma 2 and derive theorem 3 from lemma 1 and lemma 2. Like this is really how we humans work. We split it into sub-problems and solve these independently, and then we combine them. This is what our graph of thoughts work was. Okay, quite cool. So now we are at reasoning language models. Now it gets interesting. So how do we now get to these thoughts? This is not so clear, right? So this is, what is a thought even? It took me forever to discuss this with my students. So let's make a detour to a very famous game. And the game is very famous in Asia, and it's the game of Go. And you probably all remember, or many of you remember 2016, Lee Sedol, the 18 times world champion, considered the best Go player at the time, was beaten by a machine in a very public endeavor. It was live televised, and there's a documentary on it, which I recommend watching. It's very, very good. And that was a game changer because Go is a game that you can explain to every child. It's very, very simple. It's like sorting. Like you can explain to any child how to sort. But to play it, it's extremely strategic and complicated. Like the rules you can explain to everybody, but it's very hard to become a good Go player. So Lee Sedol made a career out of it, and he resigned from that career after he was beaten by the machine. So how do we run this on a machine? Well, we represent the state of the board as a state, right? And then we apply a so-called policy function to derive a new possible state. So basically, this function gives me a move that I can make. And then, of course, I invoke this policy function m times to get m possible next moves, like for my Go game, right? What I do then is I call another function, it's called a value function, to assess the likelihood of winning after making these m possible moves. Right? If you know Go, there's a very large number of possible moves, so you just sample a small subset m of those, and then you ask for each of those resulting states, what's the likelihood of winning? We assume that these two functions are just good. Like we'll not talk about how we get to them. Then we take the highest likelihood of winning, and then we do the same thing again. We are invoking the policy function again, and we get m possible next moves. Of course, we get a new states, and we invoke the value function again. Then we realize, oh, now this was probably a bad path. Now we go back up here because the probability of winning is higher than any down here. We repeat this thing, and we keep going. Right? So this is exactly how the Go game worked at the time, and that beat the best human player with a lot of training. So what turned out that the revolution was these two functions, the policy function and the value functions, were both deep neural networks. simple MLPs actually. And they trained it with a technique called Monte Carlo tree search. Right? And I don't want to go into too much detail, but it was a vast computational experiment. So they ran a lot of computation. They just simulated a lot of moves. Actually, AlphaGo was inspired by humans. Later, they came up with what they call AlphaZero, which is not inspired by human moves. It didn't try to imitate human players. AlphaZero actually performs significantly better than AlphaGo. A very nice example that humans are not developing the best strategies. So if you start from human knowledge, the resulting AI model is worse than if you start from no knowledge and just computation. I keep that in mind. Because now we are going to take this and apply the same principle to sorting the numbers. You'll see where this goes. We have a policy function, which is now a deep neural network, that outputs the next possible step. What to do with these numbers. So here, numbers are blue. That's obviously stupid. But hey, look up quicksort. That sounds like a good idea. Sorting is simple. That's kind of stupid. Split into two balanced sets. Hey, that may be a good idea. We have a value function that evaluates these possible next steps, right? And then we keep going. We do exactly the same thing. Oh, look up quicksort. Sounds good. Quicksort. What is quicksort? Now it turns out that actually for these couple of numbers, it's not a good idea to do quicksort because it's just very simple. You could do this. It realizes it down here. Basically, it just says, oh yeah, let's split them into two sets. Let's move forward. And so that's actually a real language model experiment. You do the same thing as with a Go player, right? You just play it with language models. Like, so now the policy function is a language model, and the value function is a language model. The value function is a language model that outputs a score instead of the next token. It's not a regressive language classification model, basically. That's crazy. So now you can play the knowledge base with itself, right? So that's quite nice. And this is the same MCTS technique that I just talked about. There are many, many more tricks that you do. Actually, this is more like a reinforcement learner. So you would generate a lot of traces with MCTS and then run reinforcement learning on top of this. But I'm skipping all of those details because I only have 1 hour for the whole talk. But you now see what's happening. And now you can actually look at this in practice. So if you ask Gemini Flash Thinking, sort the numbers, and I give you exactly that sequence, it'll say thinking, and it'll output the steps what it thinks about to sort these numbers, right? And then it gets you the right sequence. Actually, if you look through these steps, it's quite funny. It's like a human would do it, right? It's like, I do understanding the goal, identifying the data, pre-processing, choose an algorithm, applying a sorting method, do it step by step, look if it's correct. All of these steps that humans would do, the model now does because these steps exist in the internet, right? Because somebody has written down how to do sorting. Like, this is quite cool if you think about it. Okay, now it comes the surprise. How good is that really in practice? Well, in November 2024, there was a group of people that basically got upset that math problems were too simple. So they defined a very, very hard math data set for language models, frontier math. Indeed, most of the models at the time performed pretty poorly at it, so solving less than 5% of the problems. Even Terence Tao, a Fields medalist, so one of the highest honors in math, actually the highest honor, said in November 24, these are extremely challenging. This will last several years. Well, the reasoning model in December 24 already solved 25% of those tasks. And if you look at those, they're really, really hard, even for humans. A second example is the ARC challenge. The ARC challenge is a hard test for AI systems requiring human-like generalization capabilities from very few examples. So you can see here the timeline, 2019 to 2024, basically nothing happens in the score. Like, so all of these GPT models, including GPT-4o, did not manage to solve those. But then the reasoning models happened. And boom, this challenge is solved just with reasoning models. If you're thinking you're a clever programmer, give up because the reasoning models are at 99.95% of the ELO rating, which is kind of a chess game for programmers. So it's like a competitive programming game. Also, if you're a graduate student, well, you know, these reasoning models are doing really well and actually compare well with human PhDs in many, many fields. So how did that all happen? Well, it happened because we combine superhuman strategy playing, beating the best Go player, with superhuman knowledge, because any of these models has more knowledge than every single human. Right? And now if we combine these two, that's quite interesting. So we are now in the era of reasoning scaling. We went from data scaling to model size scaling to reasoning scaling. And the good news is, actually, if I had time, but I'm severely running out of time here, we could play this game and you would be able to beat the reasoning language model, at least at the time in that game. So we are not really done yet. So we're actually working on this in my group. So we published a paper, Reasoning Language Models, a Blueprint. So if you want to understand all the details of reasoning language models, that's a very recent paper from January. You could go through this and look through this. It's in much more detail than I'm explaining this here today. And basically, I could give you more evidence here, but I think I want to skip this. I want to just go very fast, that these three eras actually existed: model size scaling, data scaling, reasoning scaling. Because you can see it at the price per token or per 1 million tokens in the OpenAI API. I did a historic search, looked for the price. You could see the price was going up because the models got bigger and bigger and more powerful. Then there was a period where the price actually went down because now they had higher training costs but lower serving costs. And now there is a new period. If you're using reasoning models, the price goes up again for inference. And now what this basically does, it concludes that we need cheaper compute, right? So we really need to make this compute much faster. And now I would have another part of my talk to talk a little bit about Ultra Ethernet, but I want to skip this in the interest of time because we are really running out of time. So let me skip that part. So this would be talking about how we could make the network more cost effective at an international effort that's called Ultra Ethernet. But again, I want to skip it because I want to take some questions and some of you probably have to go. So I basically talked about the 1,000 times speed up we could achieve for large scale super learning. I talked about the whole history of language models that developed to this, and also